Hello everyone, this is part 2 of topic 6 for exam 1, integrals resulting in natural logs. We saw the little flowchart on how to determine if we have a situation where we're going to try to fit the form of du over u. And that's basically, once again, just asking the question, do we have a fraction? And if we do, is the denominator a power? And if it is, it's going to be a calc 1 situation, integral of u to the n. And if the denominator is not a power, then we're going to try to fit the form of du over u, which results in the natural log of the absolute value of u, plus a constant, of course. So we saw these 4 examples, basically all the different types: algebraic, trigonometric, exponential, then kind of a special case. And now we'll see a couple of other situations that are special as well. In particular, when you have a logarithm in the integrand. Now, we're going to be studying the different classes of functions, and logarithms are one of the most sophisticated. We've seen at this point, here's a little acronym that will become a hierarchy for us, giving us the 5 main classes of functions. L stands for log, I for inverse trig. We'll get to that in the next exam. A is for algebraic, T is for your standard trigonometric, and E represents the exponentials. So we say Lie8, and that'll become a hierarchy for us with a special method of integration later on in the course. But right now, what I can tell you is that if there is a logarithm in the integrand, you pick it or the quantity associated with it to be your u. And if you're lucky, the du will be there. And so in example number 9, we see a situation where there is a log involved. And we know that, and our strategy is going to change, but I can tell you once again, if there is a log involved, one chance is to pick it to be your u. And hopefully the du will be there. And we do know that the derivative of the natural log of x is 1 over x. And that's primarily why there's this x in the denominator. So instead of writing this as the natural log of x as a quantity to the 5th over x, I'm going to choose to rewrite it as 1 over x times the natural log of x as a quantity to the 5th with respect to x, to highlight the fact that the 1 over x is the derivative of the natural log of x, and it's kind of isolated there. And now I'm going to choose my u to be the natural log of x. I don't want to choose it to be the power, because if I choose u to be the natural log of x, this is then fitting the form of u to the n, or in this case in particular, u to the 5th. And so, calculating the du, it's 1 over x times the differential dx. There's no modification by a constant multiple necessary. And we can see that the leftover factors, the 1 over x combined with the differential dx, identically do make up our du. So we could replace those by du. And then we just have, upon the change of variables, the integral of u to the 5th with respect to u, which we can then integrate u to the 6th over 6th, add our constant of integration at that point, and then back substitute. So I'll write 1/6 and putting back u in parentheses the natural log of x quantity to the 6th plus our constant. So that's a special situation when a log is involved. In number 10, we have a fraction, and the denominator is not a power, but if we think about it, we want if it's going to fit du over u, the derivative of the denominator has to be the numerator. And the derivative of x is 1, and there's a 1 in there, but we've got way too many extra terms. So this is a nice problem because what it requires is an algebraic modification. This single term in the denominator we could refer to as a monomial. And when we have a monomial in the denominator, it's essentially a basic rule of arithmetic, but algebra as well, of combining fractions. That is, if we have, let me do it up here, a over c plus b over c, we know we can keep the denominator and combine the numerators. So what we're going to do here is use that rule in reverse. This monomial denominator will divide into each term of the numerator. And this rule can be extended to more than 2 terms. So basically, I'm going to divide everything in the numerator by the denominator x. So the x squared gets divided by x, gets divided by x, and 1 gets divided by x. And parentheses were really necessary there because I split it up as a sum of terms. And so, mathematically, to be correct, parentheses are necessary. Now we'll simplify. This becomes x squared over x is just x. X over x is 1. And to make sure I understand that I'm about to integrate, I'm not going to rewrite 1 over x because that fits the identical form that is integrable and turns into the natural log of x. Now, you can integrate these term by term at this point. If you wanted to, you could separate it into 3 integrals. The integral of x with respect to x plus the integral of 1 with respect to x plus the integral of 1 over x with respect to x. Or you could have skipped that step and just jump right in and integrate. This is x to the first, integrates to be x squared over 2, plus integrating 1 with respect to x, we get x, and then integrating 1 over x, we get the natural log of the absolute value of x, and then we'll add our constant. So, excuse me, that's a special case. All right, moving on, we have the first fundamental theorem of calculus, definite integrals. If we have a function that's continuous on a closed interval, okay, these things we've always kind of assumed in Calculus 1. We never really checked for continuity of the function and the interval being closed. But we'll get to situations later in the course where these are not true. But as long as those conditions are satisfied, recall the limit from the integral from a to b of the integrand lowercase f of x with respect to x is equal to uppercase f of x, where uppercase f is the antiderivative of lowercase f, and that's indicated here, evaluated from a to b. And then the fundamental theorem just says plug in upper limit of integration, so evaluate the antiderivative at b, that is uppercase f of b, and then from that subtract the lower limit of integration plugged into the antiderivative, so subtract uppercase f of a. And this, as I said, is the statement that tells us that uppercase f is the antiderivative of lowercase f, because the derivative of the antiderivative has to give us the original function, or the integrand. Okay, here's a simple integration, calculus 1 integral, just to get us warmed up, and it is readily integrable. So I'm just going to jump right in term by term. X squared integrates to be x cubed over 3, plus 1 integrates to be x. Evaluated, no constant of integration, it's evaluated from 1 to 2. And then the fundamental theorem says upper limit goes in, so plug a 2 in for x. 2 cubed over 3 plus 2, and then minus lower limit goes in. So 1 cubed over 3 plus 1, minus that quantity, that is. Okay, so then just arithmetic. This gives 8/3 plus 2 minus 1/3 plus 1. Let me do common denominator. 2 is 6/3 plus 8/3 would be 14/3, and then minus 1/3. 1 is 3/3, so minus 4/3, and that gives us 10/3. Now, just to mention this, for this particular integral, recall that if the function is non-negative, so since our integrand f of x equaling x squared plus 1 is greater than or equal to 0 on the closed interval from 1 to 2, then our interpretation is that this represents the area under the curve. So just to illustrate this for fun, let's draw the graph. Okay, when this is just a parabola passing through the point 0, 1 as its vertex. When x is 0, it's 1. When x is 1, it's 2. When x is 2, 2 squared is 4 plus 1 is 5, so 3, 4, 5. Just a rough sketch. Then we have symmetry, of course. -1 is 2. -2 is 5. So it's just a parabola, concave upward, again, vertex at the point 0, 1. So that's f of x equaling x squared plus 1. So what we just found is that the area between the graph of this function, the x-axis, and the vertical lines x equaling 1 and x equaling 2, that shaded area there is 10/3. Okay? So it's kind of nice just to recall what it means. But in terms of our interest, we're going to deal with situations involving things that result in natural logs. And in question 2, we're given a situation where there's a fraction and the denominator is not a power. So we have to think du over u, or in particular, since there's only an x in the denominator, 1 over x. Now the 5 may be bothering you then. So remember what we said. If there's a constant multiple in the numerator that's clouding the issue, you're allowed to factor out those constants from the integration process. So this would be 5 times the integral from 1 to the upper limit here is e cubed of 1 over x with respect to x. And then we could immediately integrate, so 5 natural log absolute value of x evaluated from 1 to e cubed. And now the fundamental theorem of calculus, upper limit goes in, 5 natural log absolute value of e cubed, minus lower limit goes in, 5 natural log absolute value of 1. We could simplify further. E cubed is positive, so drop the absolute values there. Obviously 1 is positive as well, so we can drop the absolute values. Now I designed this problem so some pretty things happen. 2 really nice things. In the first term, you should recall the inverse property that the natural log of e to the x is equal to x. So that was our inverse property. So therefore the natural log of e to the third is just 3. And then here we have minus 5. And you should know that the natural log of 1 is equal to 0. So if you left it, that would take off credit. So that's going to be 0. And so it looks like 5 times 3, or 15. Okay, so then in the last problem, we see something a little bit more interesting, and that is a fraction where the denominator, so we ask, is it a fraction? Yes. Is the denominator a power? No, it's not. It's just a function of x. So then we're going to try to fit du over u by choosing u to be the denominator. See, this is the type where you could tell by inspection it's going to work, because if you're trying to fit du over u, you're just basically checking to see, is the numerator the derivative of the denominator? And we could mentally see the derivative of the denominator is 4x cubed, and there's the x cubed that we're going to need to satisfy the du. But we follow through with the particulars off to the side by choosing u to be 1 plus x to the fourth. We have du is 4x cubed. Don't forget differential dx. Modify, we get 1/4 du is x cubed times the differential dx. And at that point, we plug in we make the change of variables, that is, we were trying to fit du over u, u is the denominator, the x cubed dx that remains, compare it to our du, and that makes up 1/4 du. So all factors are accounted for, we can make the change of variables. Alright, this is a subtle point. There's two, I'm going to make the change of variables first, and then we have to talk about the limits of integration. Okay, so I get 1/4, bring that out in front, and then we have, upon the change of variables, du over u. Now, because I made the change of variables, it is not proper to say, to carry along these limits of integration from 0 to 4. Because those limits of integration are in terms of the x variable. And if I change to be in terms of u, then 0 and 4 would not be correct. So there's two ways you can go about this. But I'm going to only show you the one way that I prefer. The first way, which you can try on your own if you like, is to change the limits of integration to be in terms of u. And that's not hard. You just plug in the 0 for x and you get 1 for u, and you plug in the 4 for x and you get whatever, 65, I guess. And then you would have to evaluate the integral in terms of u. But I'm not going to carry along 0 and 4 because I know that's wrong. So I'm going to use this method where I'm going to use dummy letters. I'm going to use a and b to hold the place values. Because the whole idea is that we are trained to back substitute. So I'm going to integrate as normal, and then after I back substitute, then I'm going to use the original limits of integration. So these a and b, they just kind of hold the place values. Because then we integrate, we get 1/4 natural log absolute value of u, evaluated from a to b. Now we're going to put back the u, so 1/4 natural log absolute value 1 plus x to the fourth, evaluated. Now I can say I'm going from 0 to 4. Okay, so then upper limit goes in, 1/4 natural log absolute value 1 plus 4 to the fourth, minus lower limit goes in, 1/4 natural log absolute value 1 plus 0 to the fourth. Just do the arithmetic here. 1/4 natural log. Okay, 4 to the 4th, probably use your calculator, but that's what? 4, 16, 64, 256, plus 1 is 257. The absolute value of that is 257 as well. And then minus 1/4 natural log of, looks like just 1. And then once again, note that the natural log of 1 is 0. And if you type this in on your calculator, you would get the decimal answer. So just leave it as it is, 1/4 natural log of 257. And so that's how we deal with U substitutions and definite integrals, by using those dummy letters. And that illustrates a good example of an integral that results in natural logs. So that's the end of topic 6. And we'll come back when you're ready with topic 7.